We're going to do the same thing now with the cosine function. We're going to show that for the cosine function, that this remainder, the nth remainder, is going to go to 0. So again, we'll let d be any arbitrary number bigger than 0. Note that the nth plus first derivative is either, we're dealing with the cosine function, so the derivatives just cycle. Cosine, negative cos, sine, cosine, negative sine, etc. Hope I said that in the right order. But regardless, so the magnitude just bounces between sine and cosine, sine and cosine, sine and cosine. And so this is either sine of x or cosine of x. And so what does that mean? Well, it means that the nth plus first derivative is going to be either sine or cosine, so it's bounded above by 1. And that's for any x smaller than d. In fact, in this case, we have it's true for any x because sine and cosine are bounded above by 1. So this is true for any x in the interval bounded above by d. So by Taylor's inequality, since we bounded the n plus first derivative, inequality with, in this case, m is equal to 1, a is equal to 0. So Rn of x is smaller than 1 over n plus 1 factorial. There's the m value being 1 on top. Magnitude of x to the n plus 1. This is true for x smaller than d in magnitude. What about the limit? Well, as we go to infinity, we get that this is bounded above by the limit as n goes to infinity of x to the n plus 1 over n plus 1 factorial, and that's 0 for x smaller than d. But there was nothing special about d here. The fact that we used d was really just so we could talk about things on an interval, but there was nothing special about the size of this interval. That d never actually factored into our discussion at all, so that d could be anything. And so what we have is that this limit is actually true for x smaller than d. In fact, it's true for all x in R. There's nothing special about d. And so therefore, cosine of x is equal to the sum of n equals 0 to infinity, negative 1 to the n, x to the 2n over 2n factorial. That was our series Taylor series representation of cosine, and we have that they're actually equal then for x, any real number in the interval negative infinity to infinity. Why do we know they're equal? Because we've just shown that their difference, the difference between cosine and any truncation of this, any polynomial where we just truncated at the biggest term, the difference between those two goes to 0. So as we add more and more terms of our series, we get closer and closer to cosine. That's what it means for the remainder to go to 0, that the series eventually approaches cosine. And so in the limit, we have equality.